Waves. What waves do? Waves transfer energy and information from place to place without transferring matter. The water, the air, the rope, they all just vibrate on the spot and let the energy pass through them. If you imagine a Mexican wave going round a stadium, the wave races around the grounds, but every person stays in their seat. The energy moves, but the people don't. Transverse and longitudinal. There are two types. In a transverse wave, the vibrations are at right angles to the direction the wave travels. If you flick a rope up and down, the wave moves along, but each bit of rope moves up and down. Light, all electromagnetic waves, and water waves are transverse. In a longitudinal wave, the vibrations are along the same direction that the wave travels, and they make squashed up compressions and spread out rarefactions. If you push and pull a slinky, the pulse travels along while the coils bunch up and stretch out. Sound is an example of a longitudinal wave. Wave properties. Amplitude is the maximum displacement from the rest position. Bigger amplitude means the wave transfers more energy, and AQA like the phrase maximum displacement. Unlike sound, electromagnetic waves do not need a medium. They can travel through a vacuum, and this is a very common exam question. Sound travels fastest in solids, slower in liquids, and slowest in gases because the particles are closest together in solids. AQA asks this surprisingly often. Wavelength is the distance for one full wave, from peak to peak or trough to trough. Frequency is how many waves pass a point each second, and it's measured in hertz. Period is the time for one wave to pass in seconds. Frequency and period are two sides of the same coin, linked by an equation. Period equals 1 divided by frequency. In letters, that's T equals 1 over F, where T is the period in seconds and F is the frequency in hertz. Walk 1 through. A wave of a frequency of 4 hertz has a period of 1 divided by 4, which is 0.25 seconds. In the exam, get a time into seconds first. If you're given milliseconds, divide by 1,000. Wave speed. Wave speed is how fast the wave travels, and it links to frequency and wavelength with one equation. Wave speed equals frequency times wavelength. In letters, that's V equals F lambda, where V is the wave speed in meters per second, F is the frequency in hertz, and lambda is the wavelength in meters. Let's walk 1 through. A wave has a frequency of 20 hertz and a wavelength of 3 meters. So you multiply 20 by 3, which is 60. So the wave speed is 60 meters per second. The other way, a wave travels at 320 meters per second with a frequency of 80 hertz. So to find the wavelength, you rearrange to wavelength equals wave speed divided by frequency, which is 320 divided by 80, which equals 4 meters. In the exam, check frequency is in hertz and wavelength in meters before you multiply. And remember, every wave, sound, water, and light obeys this same equation. Required practical, measuring wave speed. You measure wave speed 2 ways. For water waves, you use a ripple tank, and a dipper makes ripples, and a light above casts the pattern onto a screen below. Measure across several waves and divide to get the wavelength. Count the waves passing a point for the frequency. Then, use wave speed equals frequency times wavelength. For waves on a string, run a string from a vibration generator over a pulley with a mass to keep it taut, and turn up the frequency until a clear standing wave appears with still points. The wavelength is twice the distance between 2 still points. Read the frequency of the generator and use the same equation. In the exam, always measure across many wavelengths and divide, never just one. It cuts your percentage error right down. And refraction. When a wave meets a boundary, it can be reflected, bouncing off, which gives you echoes and mirror images. It can be absorbed, its energy transferred into the material, which is how microwave heats food. Or it can be transmitted, passing through and usually changing direction, which is refraction. Refraction happens because the wave changes speed in the new material. Slow down and it bends towards the normal. Speed up and it bends away. The change in speed is the cause and the change in direction is the result. And a wavefront diagram shows the fronts bunching closer together in the slower material. The electromagnetic spectrum. Visible light is one small slice of a much bigger family, the electromagnetic spectrum. They're all transverse, they all transfer energy, and in a vacuum, they all travel at exactly the same speed. 7 groups, and you need them in order: longest wavelength and lowest frequency first, radio, microwave, infrared, visible light, ultraviolet, X-rays, gamma rays. Remember it with raging Martians invaded Venus using X-ray guns. Along that list, the wavelength gets shorter and the frequency gets higher and the energy bigger, which is why the gamma end is the most dangerous. Uses of electromagnetic waves. Radio waves carry television and radio. Microwaves do mobile phones, satellite signals, and heating food. Infrared for cooking, remote controls, and thermal cameras. Visible light is for seeing and photography. Ultraviolet is for security marker pens and tanning. X-rays see inside bodies and luggage. And finally, gamma rays sterilize equipment and treat cancer. Dangers of electromagnetic waves. The high energy end is the harmful end. Ultraviolet damages skin cells and can cause skin cancer and eye damage, hence sun cream and sunglasses. X-rays and gamma rays are ionizing. They knock electrons off atoms and damage the DNA in cells, which can cause mutations and cancer. More radiation and longer exposure means more risk, which is why radiographers step behind a screen. Sound waves. Sound is a longitudinal wave made by something vibrating. The vibrations pass through the air as compressions and rarefactions until they reach your ear and make your eardrum vibrate. And your brain reads that as a sound. Because sound needs particles, it can't travel through a vacuum. So space is silent. Humans hear roughly 20 Hz up to 20,000 Hz, and that range shrinks as you age. Ultrasound and seismic waves. Sound above 20,000 Hz is ultrasound, too high for us to hear. It's used for medical scans like seeing a baby in the womb and for spotting cracks in metal. It sends in a pulse and times the echo coming back to work out how far away a boundary is. Earthquakes make seismic waves. P waves are longitudinal and travel through solids and liquids. S waves are transverse and only travel through solids. S waves, solids. Because S waves can't cross the liquid outer core, we know that part of the Earth's core is liquid. Lenses. A lens forms an image by refracting or bending light as it passes through the glass. A convex lens, also known as a converging lens, is thicker in the middle than at the edges. It bends parallel rays of light inwards so they meet at a point called the principal focus. The focal length is the distance from the centre of the lens to the principal focus. A shorter focal length means the lens bends light more strongly. A concave lens, also called a diverging lens, is thinner in the middle than at the edges. It spreads parallel rays of light apart so they appear to come from a point behind the lens. A convex lens can produce two different types of image. If the object is further away than the focal length, the rays actually meet on the other side of the lens. This forms a real image, which can be projected onto a screen like in a projector or camera. If the object is closer to the lens than the focal length, the rays leave the lens spreading apart. Your brain traces them back to a point behind the lens, so you see a virtual image. This image is upright and magnified, which is how a magnifying glass works. A concave lens always produces a virtual, upright and smaller image because the rays never actually meet. Magnification tells you how many times bigger the image is than the object. The equation is magnification equals image height divided by object height. Let's walk one through. An object 2 centimeters tall forms an image 6 centimeters tall. So you do 6 divided by 2, which is 3. So the magnification is 3. The image is 3 times bigger. Magnification has no units because it's just a number of times. In the exam, keep both heights in the same unit before you divide. And a magnification less than 1 means that the image is smaller. Visible light and colour. White light is a mix of all the colours. An object looks the colour because of the wavelengths it reflects. A red jumper reflects red and absorbs all the other colours. White reflects everything. Black absorbs everything, which is why black things heat up in the sun. Filters let some colours through and absorb the rest. A red filter only allows red to pass through. In the exam, a red object under green light looks black because there's no red light for it to reflect. Black body radiation. Black body radiation is the electromagnetic radiation given off by all objects because they have a temperature. A perfect black body is an ideal object that absorbs all the electromagnetic radiation that falls onto it. It also emits radiation better than any other surface. For a steady temperature, an object must emit energy as fast as it absorbs it. Absorb more than it emits, and it warms up. Emit more than it absorbs, and it cools. That balance sets the Earth's temperature, and tipping it drives climate change. As an object gets hotter, it emits more infrared radiation, and the peak wavelength becomes shorter. This is why a piece of metal first glows dull red, then orange, then yellow, and eventually white as its temperature rises. You can show it with a Leslie cube. The matte black side emits the most infrared, the shiny silver side the least. In the exam, you could be asked why matte black surfaces are used on radiators or solar panels. The answer is that matte black surfaces are very good absorbers and emitters of infrared radiation. Shiny, light-coloured surfaces are poor absorbers and emitters, but good reflectors. You may also be asked to compare two objects at different temperatures. The hotter object emits more radiation overall and has a shorter peak wavelength than the cooler object.